Today we will continue with X-Ray Resonant Magnetic Scattering. It is an absorption experiment. The name here you see scattering, but it is an absorption experiment. I will go into detail, and by using this method, we will investigate the magnetic properties of the matters. How it looks, here we have a magnetic material. It has certain magnetization in the film plane, and this is the incident photon, X-ray beam, comes to the surface with some certain theta angle, and it is reflected with some certain 2 theta detector angle. Okay, this is the detector waiting here. Actually, we are investigating the photons produced by the material. Remember the absorption mechanisms: fluorescence X-rays, photoelectrons, and Auger electrons. Here, in this type of method, we have incoming X-ray beam, and here we have an electron in the certain orbit. And if the energy of the incoming X-ray beam, X-ray photon, is higher than the binding energy of the electron here in this orbit, then it can be excited, and another electron will drop to this level. Then the atom will emit an electromagnetic radiation, fluorescence X-ray, and this will be detected by the detector. Okay, so this is the main mechanism of X-ray resonant magnetic scattering. So what do you see here? That you have to choose a correct energy of the incoming photon in order to excite this one, in order to overcome the binding energy of this electron. This is very important. And since this mechanism occurs at the energies of the binding energies of the electrons, this is an absorption experiment. Okay, so what we have within this method, what are the advantages if we use this method? The magnetic properties of multilayers and interfaces can be determined. So here in the picture you see just single layer, but if you have multi-layer system and if you have different interfaces between the layers, you can selectively study the magnetic properties of these layers and interfaces. So this is the unique property of the Xrms method. In addition to that, of course, you can apply magnetic field to the sample in the film plane during this type of measurements. And one of the main advantages of this method is that you can measure the hysteresis curves of each magnetic element within the material. If you have a multi-layer system, let's consider here you have an iron, here you have a nickel, and here you have a cobalt ore, here you have coffee B, cobalt, iron, boron alloy, for example. You can investigate hysteresis loop of each layer separately. So you can carry out element-specific hysteresis loop measurements. Okay, this is the very nice property of this method. So what is the hysteresis curve? Hysteresis curve carries information about the magnetic properties of the materials. Okay, so I will go into detail. Of course, in order to analyze the hysteresis curves, hysteresis loops, you have to be familiar with the magnetic properties of the materials, but this is not the topic of this lecture. The magnetization is discussed in solid-state physics lectures and also discussed in a separate course with the name of magnetic materials. So within this lecture, I will only use this previous information. And during the measurements, we use longitudinal Mach geometry, and I will explain what is this longitudinal Mach geometry. Let me start with the magneto-optical effects. Here, I told you that during this measurements, longitudinal Mach geometry is used. Mach is Magneto-Optical Kerr effect. So what do you see here? Magneto-optical. So we have relation between magnetization of the sample and optics. Okay, so we have X-rays, we have optics, and we are investigating the magnetic properties, so magneto-optical effects. You can consider like this. So what is the origin of this magneto-optical effects? In 1845, Michael Faraday did an experiment. He used polarized incident photon, laser beam, let's say, okay, or you can consider white light, and it is polarized. It has certain polarization. And here there is a material, magnetic material. If a polarized light passes through this magnetic material, its initial polarization is rotated with some certain angle, which is called as Faraday angle. Okay, if the polarized incident photon passes through this magnetic material, and if its initial polarization is rotated with some certain angle, then this effect is called as Faraday effect. And this theta angle here, look at the incident polarized light. This is the initial polarization, and this is the final polarization. So we have here theta Faraday, and this Faraday angle is proportional to the magnetization of the material. So by measuring the Faraday angle, you can get idea about the magnetization of the material. So then magneto-optical effect, okay? Later on, in 1877, John Kerr discovered that the reflected light from the surface of the magnetic material can also carry information about the magnetization of the material. So he did this experiment. He used incident polarized light. The incident light has certain polarization, and it is reflected from the surface of the magnetic material. And he discovered that the initial polarization is rotated with some certain theta angle, and this angle is called as Kerr angle, theta Kerr, and the method is, or the effect is called as Kerr effect, okay? And later on, this effect is called as magneto-optical Kerr effect, okay? If you are measuring the reflection of the incident polarized light from the magnetic material. And the details of the magneto-optical effects can be found in this master thesis published in 2004. So I will not go into detail here. I have told you that during the Xrms experiments, longitudinal Mock geometry is used. What is the meaning of longitudinal Mock? I have already explained the Mock. You have incident polarized light, and it is reflected from the magnetic material, and then its initial polarization is rotated with some certain Kerr angle. Okay, so this is the magneto-optical Kerr effect. But what is longitudinal Mock? So we have three different Mock geometries depending on the measurement condition and depending on the magnetization within the sample. We have polar Mock, short name is P Mock, but we have, this is the thin film, this is the surface of the thin film, and we have magnetization perpendicular to the surface of the thin film, okay? This thin film is a magnetic, okay? And its magnetization is perpendicular to the film surface. And this is the incident photon, this is the reflected photon. So look at this one. This incident and scattered or reflected photon produce a scattering plane. This plane is called a scattering plane. So what do you see here? In case of polar Mock, this magnetization vector is in the scattering plane, parallel to the scattering plane, but it is perpendicular to the sample plane, okay? In case of polar Mock, magnetization vector is parallel to the scattering plane, but it is perpendicular to the sample plane. In case of longitudinal Mock or L Mock, here we have scattering plane, photon comes and reflects from the surface. So what we see here, this magnetization vector again parallel to the scattering plane. M is parallel to the scattering plane. What do you see here? Magnetization vector is also parallel to the sample plane. Then this is called as longitudinal Mach. The magnetization of the material is in the sample plane, and it is also parallel to the scattering plane. So what we have in the transverse Mach, we have magnetization. The magnetization is again parallel to the sample plane, but look at the scattering plane. Magnetization is perpendicular to the scattering plane. And we have this condition. Magnetization is perpendicular to the scattering plane, but it is parallel to the sample plane. So depending on the direction of the magnetization, we have three different Magneto-Optical Kerr effect geometries. Okay, so for different purposes, we use different Mach geometries. And in case of Xrms experiments, we use longitudinal Mach geometry. Okay, so we will continue with this geometry for the Xrms experiments. Then let me continue with the Xrms measurement setup. Here we have Xrms measurement setup. So you can carry out these experiments by using synchrotron radiation, okay? Or you can carry out this type of experiments by using free electron laser radiation, okay? It depends on the beamline properties, okay? Beamline properties are very important in case of Xrms experiments. I will go into detail, but here let me tell you that we need to change the polarization. We need to change the energy of the incoming photons. For this reason, you need synchrotron radiation. In addition to that, high intensity is very useful in case of these experiments. So synchrotron radiation is obligatory in case of these experiments. You cannot carry out this experiment in the lab, okay? So here we have synchrotron light source here on the left corner, okay? This is the synchrotron accelerator booster. This is the storage ring. And here we have undulator, monochromator, and beamline and end station. So this is the end station. This picture here, end station, okay? This is the beamline. This part is beamline. X-ray comes from the beamline, from the undulator and monochromator, and enters into the experimental setup. What I have told you that in case of Xrms experiments, we are using L-Mach geometry, longitudinal Mach geometry. So look at the incoming X-ray beam. Incoming X-ray beam comes with some certain angle, theta angle, and it is reflected from the surface and it goes to the detector located here. Okay. Here we have a material, here we have a sample, and we can apply magnetic field by using this magnet poles here. Okay, here we have magnet poles, and we can apply magnetic field in this direction or in opposite direction, and we can also manipulate the magnitude of the magnetic field because we are using an electromagnet. Okay, so look at this geometry. Magnetization is in the film plane, and magnetization is parallel to the scattering plane and also the sample plane. So this is the L-Mach geometry. Okay. So what we have within this setup, this is a vacuum chamber, and as much as I remember, the vacuum within the chamber is 10 to minus 7 millibar, but it can also reach to 10 to minus 8 millibar, or sometimes 10 to minus 9 millibar, okay? Depending on the vacuum pumps and depending on the time you pump the system. So we have vacuum within the chamber. Why we have vacuum? remember the synchrotron light sources, remember the beam lines, this X-rays can be interacted with the gas atoms in the air, then they can lose their energies or they can be diffused, scattered, okay? So in order to avoid all the things, we have to use good vacuum conditions within the beam line and also within the measurement chamber, okay? So we have at least this vacuum within this chamber. And here we have a fluorescence screen. Here with this screen, you can see the direct light. It is related to the sample alignment. So before this measurement, you have to align the sample as we have discussed during the last lecture in X-ray reflectivity experiments. And also before the X-ray diffraction experiments, we have to carry out sample alignment, and you have to carry out also sample alignment in case of Xrms measurements. So then you need a good diffractometer. You need to move the sample in and out. You need to rotate the sample and change the angle of the sample. You need to rotate the detector and you need to change the position of the detector, okay? So, and also in order to keep the external magnetic field always parallel to the sample plane, you also have to move the electromagnet, okay? So we have a good goniometer here. We can change the detector angle, we can change the sample angle, and we can change the sample position in and out. And what else? We can change the position of the electromagnet. At least we have 5 or 4 parameters we can change by using a very precise goniometer, like in X-ray diffractometers. And here we have a load lock window. You can open it, you can install your sample here, and you can remove your sample, or if something went wrong, you can repair, you can work within this chamber. So this is the load lock window, and with this design, maximum magnetic field can be applied with plus minus 2700 Ørsted within this chamber. Here I have plus minus sign. I am showing the direction of the magnetic field, okay? So maximum field along this positive direction or maximum field along this negative direction. And since we are using electromagnet, we can also apply 0 or let's say 1 Ørsted or 100 Ørsted, 1000 Ørsted, okay? You can change the magnitude of the magnetic field up to this value, and you can also change the direction of the magnetic field. And in addition to that, we have a cooling system attached to the sample, and we can cool the sample down to 4.2 Kelvin. This is the liquid helium temperature, very cold conditions. I'm talking about minus 270 degrees, more or less, okay, degrees Celsius. And we can also heat the material up to 475 Kelvin. So if you consider that the room temperature is 300 Kelvin, then we can go up to 200 degrees Celsius, okay? So this setup is designed and constructed by Johannes Grabes. He was a PhD student of my professor. Very nice machine and also open for many users, many external users from the world. And during my PhD thesis, I also work with this chamber a lot. Okay, then let me continue with the 5 important parameters that can be changed in Xrms experiments. Don't forget that I am talking about this experimental setup, okay? If you have different experimental setup, then you can have different conditions to change the parameters, okay? But at least some of the parameters are required in this type of experiments. So we can change the polarization. We are using undulator here. Okay, we can change the polarization of the incident photon. Here we have incident photon. It must be polarized. It can be right circularly polarized light or left circularly polarized light. it can be horizontally linearly polarized light or vertically linearly polarized light. So you can change the polarization by using the undulator and monochrometer relation here. The computer allows you to change the polarization and commence the undulator and monochrometer simultaneously. And you can also change the energy of the incident photon. Incident photon is coming with some certain energy, and you can select the energy, you can scan the energy. So you can do this one by using the monochrometer in the beamline, okay? Energy is very important in Xrms experiments because depending on the element, you need certain energy. Remember that the fluorescence X-rays are characteristic for each element, okay, in the periodic table. So they have certain energies. So then energy is very important in this type of experiments. I will go into detail. So we can change the sample angle and detector angle because we are using a goniometer. Here we have a sample. You can change the detector sample angle, and you can also change the detector angle by using a very nice goniometer. It is also done by the computer controlled program. And you can also change the magnetic field. We can change the direction of the magnetic field. We can also change the magnitude of the magnetic field. This setup gives us this possibility. And we can also carry out experiments at room temperature. You can carry out experiments at very low temperatures, and you can carry out experiments at high temperatures, or you can select and set temperatures between these temperatures, okay? So these are the 5 important parameters that can be changed within this setup. As I told you, at least polarization, energy, and magnetic field can be changed during this type of measurements. But if you have freedom of degree to change the sample and detector angles, and also temperature will give you very nice flexibility to carry out different types of experiments in Xrms chambers. Here I have talked about the polarization, linear polarization or circular polarization. Now let me give you some brief information about the polarization. So all these things are discussed in the optics lectures in the undergraduate courses. So here I would like to remind you, okay? So here we have a sample. Let's consider this is the sample surface, and this is the incident photon comes to the surface and it is reflected from the surface. So then this is the scattering plane, okay? This is the sample plane. And what about the polarization vectors? In an unpolarized light, we have electric field component of the light in any direction. Okay, this is a schematic representation of unpolarized light. So these are the electric field components. You know, light has 3 components: electric field component, magnetic field component, which are perpendicular to each other, and also there is a propagation vector K, okay? This is E, this is B, and this is K, propagation vector. So this electric field component can be like this in unpolarized case, or if you polarize, what is the meaning of polarization? You select certain electric field component from the unpolarized light, then you have this one. Or you can choose this one, okay? So you only allow this component of the electric field. This is vertically linearly polarized light. This is horizontally linearly polarized light. In case of circular polarization, you have both components of vertical and horizontal components of the electric field. I will talk about here. So here we have incident photon. It comes with some certain angle to the sample surface. And here we have electric field component of the light, which is perpendicular to the scattering plane. Perpendicular to the scattering plane. Okay, this perpendicular component is shown by this E sigma. Okay, E sigma is the perpendicular component of the linearly polarized light. Sigma is showing the perpendicular component, I is the incident. Okay, and if the polarization is parallel to the scattering plane, then we show it with this E pi, okay, parallel to the scattering plane. And here, what do you see? This is the reflected or final photon. Here we have E sigma final. Here we have E pi final. This is parallel to the scattering plane. This is perpendicular to the scattering plane. In case of circularly polarized light, as I told you, we have both components of sigma and pi, perpendicular and parallel components. So what do you see here? We have plus minus sign. What is the meaning of plus minus? Plus means right circularly polarized light. Minus means left circularly polarized light. Okay, RCP, LCP. So if we have RCP, then we have positive sign here, negative sign here, and positive sign here. If we have LCP, then negative sign here, positive sign here, and negative sign here. So we have 1 over square root of 2 E sigma plus minus I E pi. Okay, this is the imaginary part. And in case of circularly polarized light, we have both components of parallel and perpendicular components of the polarization. So for the details, you can visit this reference, okay, here, or you can check the optics books. I suggest to check the Hecht optics written by Hecht, very nice optics book. You can see the details of polarization and how to produce a polarized light. There are many methods to produce and select the certain polarization. In case of synchrotron light sources, polarization is adjusted by the undulator, but you have to adjust it simultaneously by manipulating the monochrometer when you are changing the energy. Here, I have told you that 5 important parameters that can be changed in Xrms experiments. So I have talked about the polarization. Now I will talk about the energy. Sample and detector angles can be changed by the goniometer. Magnetic field can be changed by the electromagnet. Temperature can be changed by the temperature controller. Okay, so the last one, energy, how to manipulate the energy. As we have discussed in the synchrotron light sources, the energy can be manipulated by the monochrometers. But why energy is required? Why we need specific energy? Because each element in the periodic table has certain specific binding energy in the orbits. Okay, for example, let's consider oxygen. The electron binding energy in the K shell of the oxygen is 543.1 electron volt. Okay, so here look at the titanium, for example. Here we have L2H binding energy, L3H binding energy. So look at this column here and look at also this column here. This is the binding energy of the L2H, 460 electron volt more or less. And the binding energy of the L3H is 453.8 electron volt. Okay, but if you go to iron, it has this binding energies. And if you investigate cobalt, nickel, copper, zinc, okay, this elements has specific binding energies for K and L shells and also for other orbits. Okay, so these energies are specific and they will help us a lot in order to investigate multilayers or alloys elements specifically by using the Xrms method. Now, let me continue with the X-ray magnetic reflectivity. This is a preparation experiment to the real X-ray resonant magnetic scattering experiments. So the method is more or less same as in the X-ray reflectivity, which you have learned during the last lecture, but here we only have a term magnetic, okay? And don't forget that in case of X-ray reflectivity measurements, which we have discussed during the last lecture, we are using hard X-rays. But in case of X-ray magnetic reflectivity, we are using soft X-rays. Why? What was the hard X-ray? Hard X-ray means that we are talking about X-ray energies higher than 2 kV. And in case of soft X-rays, we are talking about energies lower than 2 kV, roughly, okay? Let's consider you would like to investigate iron or cobalt. Look at the binding energies. Less than 1 kV, less than 1 kV. Look at the zinc. The binding energy is around 1 kV. So we are talking about soft X-ray range, okay? But in case of X-ray reflectivity experiments, which we have discussed during the last lecture, we are using hard X-rays. We are using more or less 8 kV, something like this, okay? So it is completely different. And here we apply magnetic field. So how to carry out these experiments? First of all, you have to select the polarization of the incident photon. And then you have to choose the temperature. Temperature must be fixed, okay? You have to study at a certain fixed temperature. Temperature should not fluctuate during the measurement. If it fluctuates during the measurement, your measurements will be affected because magnetization depends on the temperature, okay? For certain materials, even small fluctuations in the temperature can affect the magnetization. So if you are investigating the magnetization, you have to fix the temperature, okay? And then the energy of the photon is adjusted to the electron binding energy under investigation. So let's consider that here we have this sample structure, aluminum oxide, substrate, and zinc cobalt oxide. So here we have cobalt, which is magnetic, and you would like to investigate cobalt here. Then you have to go back to the X-ray data booklet to check the electron binding energies of the elements. Here we have cobalt, and look at the electron binding energies of the cobalt. This is L2, this is L3. So for the L2, 793, and for the L3, 778 electron volt. So you have to choose this energy. If you are studying with the chromium, for example, you have to choose this one. If you are studying with the manganese, you have to choose this one. If you have studying with the nickel, then you have to choose this one, okay? So you select the energy of the incoming photon, okay? Usually K, L2 or L3 edges of the elements. And then you have to carry out sample alignment, okay? I have discussed the sample alignment during the last lecture, okay? You have to repeat the same procedure of the sample alignment also here. And after the alignment, you measure the reflectivity curve. You remember from the last lecture. You measure the reflectivity curve. This is 2 theta, this is the intensity. But in case of X-ray magnetic reflectivity, you apply magnetic field to the sample in certain direction. Polarization is fixed. Let's consider right circularly polarized light is selected. Here I have already shown you. and then you apply magnetic field in this direction. Then you reverse the direction of the magnetic field, and then you repeat the X-ray reflectivity again. So if the sample is magnetic, there will be difference between blue and red curves in the X-ray reflectivity measurements. If the sample is not magnetic, these two curves will be identical, okay? So then the difference between the two measured reflectivity curves is proportional to the magnetization of the sample. If there is no difference, then the sample is not magnetic. If there is a huge difference between this blue and red curves here, then we have certain magnetization within the material. You can also carry out this experiment like this. You apply magnetic field in certain direction and fix the magnetic field. You change the polarization. You can use right circularly polarized light, or you can use left circularly polarized light. So you can carry out two reflectivity curves for two different polarizations, okay? Or you can fix the polarization and you can reverse the direction of the magnetic field, and you can take two reflectivity curves for two different magnetic field directions, okay? Both of them are possible. Both of them will give you the same result, but in reality, it is better to fix the polarization, then change the direction of the magnetic field, and then repeat the reflectivity curve for two different magnetic field directions. Then let me show you the real data. So this is the energy, 708 electron volt. This is the temperature, okay? And here polarization is also fixed, right circularly polarized light. So three parameters are fixed. And then I am applying external magnetic field to the sample, this black one, to the right side, and I am repeating the reflectivity curve for the magnetic field in opposite direction. And these are the two reflectivity curves here. You see, here we have black solid line, and here we have also red open circles, which are showing two reflectivity curves taken for different conditions. Okay, black one is taken with the magnetic field in the right direction, let's say. The red one is taken with the magnetic field in opposite direction. So look at the reflectivity curves. Can you see any difference between the reflectivity curves? Actually, it is not so easy to see any difference. Here, maybe we can see very small differences, okay? But it is not so easy to judge any difference between these two reflectivity curves. In order to see the difference between two curves, the best method is to plot the asymmetry ratio. Asymmetry ratio is this one. I plus the first reflectivity curve. This is the intensity, okay? Minus I minus the second reflectivity curve taken in opposite direction over sum of the intensities. So here in the inset of this figure, we have asymmetry ratio of these two reflectivity curves. Look at the x-axis. We have 2 degrees. And it starts from 0, it goes to 30 degrees. It starts from 0 to 30 degrees. So this x-axis is same, but here we have intensity. Here we have asymmetry ratio, okay? We have plotted these two curves as a function of asymmetry ratio. Then what do you see here? We have this type of behavior. And you see more or less 16% difference at certain 2 theta angle, okay? Here, in this bigger figure, you cannot judge the difference between two curves, but if you plot asymmetry ratio, then you can easily see the difference between two curves. And there is a huge difference between the curves. So we have plotted asymmetry ratio, and we can better see the difference between two reflectivity curves. What do you see here? The difference here is more or less 16% between two curves, and here we have difference more or less 13%, okay? But which angle is better for me? Here we have the angle is around 11 degrees. Here we have the angle around 8 degrees, let's say, okay? Which angle is better for us? For the forthcoming experiments, I have to choose a certain incoming angle, okay? This is the aim of this X-ray magnetic reflectivity measurements. Now, listen this part carefully. Just look at the 11 degrees here. Somewhere here, right? And look at this position. Let's say somewhere here, 8 degrees, something like this. Is it correct? I am looking for the position of this angles. And look at the intensity for this one. Look at the intensity of this one. Intensity for this point, for this 2 theta angle, is much bigger, more or less 2 times bigger compared to the intensity at this angle. Okay? So remember that in absorption experiments, in diffraction or scattering experiments, intensity is very important, okay? High intensity helps us a lot to get more information from the samples and also to carry out fast experiments. So then I choose where the difference and intensity is huge. So here we have difference between two reflectivity curves is 16% more or less, and here at this point intensity is also huge. For this reason, for the forthcoming experiments, I always fix this angle here, okay? This theta angle here, which is determined from this position. Okay, then let's carry out real Xrms experiments. The topic is Xrms. We would like to carry out Xrms experiments. We have done X-ray magnetic reflectivity measurement, and we have determined the best 2 theta and theta angles. Then just go to this certain sample and detector angles, which are determined from the reflectivity measurements, okay? The angle at which the difference and intensity are the highest. Then just fix the temperature, select certain temperature, adjust the temperature, and then select certain polarization, okay? Just let's say right circularly polarized light, let's say temperature is 300 Kelvin, room temperature, okay? You have selected 2 theta angles, which you determine from these measurements. And then, depending on the element, carry out energy scan. So we have to scan the energy. How to scan the energy? We will use the monochrometer, okay? So during this measurement, you also apply a fixed magnetic field, okay? Certain magnetic field must be applied. What you see here, energy is not fixed. We scan the energy, okay? And the energy range depends on the element under the investigation. If you are investigating zinc, you have to scan the energies around the zinc, okay? If you are investigating cobalt within the material, you have to scan this energy range, okay? So, for example, you can start from 700 electron volt to the 800 electron volt. Then you can see this transitions, this L2, L3 edges for the cobalt, okay, if you scan this range. In order to investigate zinc, you have to scan this range, okay? So here, within this material, we have zinc, cobalt, and oxygen, 3 elements. So all these 3 elements can be investigated element specifically, okay? So this is the very nice property of the Xrms method. So then the same energy region is resecant by changing the direction of the magnetic field, okay? Or you can fix the direction of the magnetic field and you can change the polarization of the light and you can carry out energy scan. So there are two methods. Here we have the real experiment. The 2 theta is 8.2 degrees. Look at this one. 8.2 degrees is this one. Okay, the best angle where we have the highest intensity and maximum difference between two curves. If 2 theta is 8.2 degrees, then theta must be 4.1. Okay, don't forget this one. So then select the 2 theta 8.2 and theta 4.1. Then select the temperature, room temperature. Select the polarization, right circularly polarized light. All these parameters are fixed. Then apply external magnetic field in the film plane like this. And then carry out energy scan. Look at this x-axis now. We are scanning the energy. Monochromator changed the incoming photon energy, okay? We started from 720 electron volt and we will go to 840 electron volt. And look at these energies. Around 780 and 790 electron volts, okay? Here in this range, something happens. This is the L3, this is the L2 for the cobalt. Okay, we are carrying out Xrms experiment around cobalt L3 2 energies. How I know this one? From these tables. Look at the L3 778, look at the L2 793. Okay, so what we see here. So around the absorption energies, we see very high intensities, okay? This is the general behavior of the synchrotron light source. It is decreasing by time, but here we see some features. What happens? Intensity at this energy is huge. So I can tell you that the detector is waiting here. And for some certain energies, more X-rays go to the detector. Why? Because at these energies, incoming photon energy is enough to produce excited electrons, and we can produce more fluorescence characteristic X-rays, okay? Then more intensity is recorded by the detector. Okay, so why we have high intensity for the L3H and why we have less intensity, I will discuss this one during the next lecture in XMCD experiments. And now let me continue. I have carried out one experiment with the external magnetic field direction. This is shown by black curve and with I+. And I reverse the direction of the magnetic field. And I repeat the same energy scan. What do you see here? This red curve is completely different from the black one. So they are not identical. It means that there is a huge difference between two Xrms data. Okay? If I plot these two curves in an asymmetry ratio, then here I have an asymmetry ratio. What do you see here? More or less 30% difference between these two curves. Okay? More or less 30% difference. Actually, you can also see here, this is the maximum intensity with the I+, okay? The magnetic field to the right side. And here we have I- magnetic field to the left side. So we have huge intensity difference. And also here you can see intensity difference. But intensity difference occurs only around the absorption energies, okay? So before the absorption energy of the L3, after the absorption energy of L2, we have nothing, okay? I will discuss the origin of this one in the next lecture in XMCD experiments because they have similar mechanisms and they can convert it to each other. So now let me discuss this data. If you have 30% difference, I mean, if you have certain difference between two data, it means that the cobalt here is magnetic, okay? We have huge magnetic signal from the cobalt. You can ask this question, why this material is important, why we are investigating this one. This zinc cobalt oxide is used to produce magnetic semiconductor. So this material can be magnetic and also semiconducting. Then they are planned to be used in spin LEDs, spin light emitting diodes, or spin transistors. Okay, so there are many efforts on this issue with different materials, with gallium manganese arsenide, with titanium cobalt oxide, zinc cobalt oxide, and also with many other different materials. Many people works on this issue, okay, to produce magnetic and semiconducting properties in a single material. And then what do you see here? That this material is magnetic. This is very nice result. And then I would like to investigate oxygen. Oxygen is normally not magnetic. It is paramagnetic, okay? It shouldn't give any magnetic signal. And then we investigate the oxygen. This is the energy scan for the oxygen. Here you see I plus, I minus, different magnetic field direction. We have Xrms experiment. And this is the oxygen KH. Look at the oxygen. Oxygen binding energy for the KH, for the K energy level is 543 electron volt. 543, somewhere here, okay? So we start before this energy and finish after this energy, and we scan this range. So between these two scans, you cannot see any difference. Okay, let me magnify. So here we have two data taken for different direction of the magnetic fields, but you cannot see any difference. But if you plot this data as a function of asymmetry ratio versus energy, so what you see here, we have nothing here, but around this absorption energy of the oxygen, we have a difference. It is very small, 0.6%. Look at this one. It was 30%. This is 0.6%. Very small magnetic signal compared to the cobalt. Okay, so but it is certain magnetic signal. It is not a noise. We have many real data here. Okay, so this signal is real. So then we have magnetic signal from the oxygen. Actually, we don't expect any magnetic signal from the oxygen. Why oxygen is magnetic? The reason is that when the cobalt sits on the zinc oxide lattice and makes bonding with oxygen, okay, we have cobalt oxide bonding, and due to this bonding, cobalt affects the oxygen P levels, and P levels of the oxygen split, then oxygen also exhibit a magnetic signal. Okay, this is not within the scope of this lecture. I will not go into detail, but you can also get this information by using the Xrms experiments. This shows us how this method is powerful. Without destroying your sample, you can investigate cobalt and you can investigate oxygen. Even you can investigate the zinc separately, okay? And you can get idea about the behavior of the elements within this alloy, within this material. And now let me continue. The last one, I would like to investigate zinc. Temperature is selected, polarization is selected, and then theta, 2 theta are selected, and I scan the energy range for the zinc. Then go back to the energy table. For the zinc, I should scan this energy range, 1045, and 1021, let's say, okay? 1045 here and 28 somewhere here. So I scan this energy range. This is the Xrms, and here I have two data for different direction of the magnetic fields, but you cannot see any difference. Then I plot the asymmetry ratio as a function of energy. What do you see here? There is nothing. Zinc is not magnetic, and I don't expect any signal from the zinc, okay? So this is the data from the zinc within this material, and I got information from all three elements in zinc cobalt oxide material. And now let's continue with the hysteresis curve measurements. Hysteresis curve is like this, and maybe you have learned in solid-state physics courses or magnetic materials courses. And this hysteresis curve carries information about the magnetic properties of the material. And the hysteresis comes from the history. Material remembers its history, okay? So once you magnetize your sample, it always repeats this behavior. For this reason, it is called as hysteresis curve. And depending on the magnetization, we have certain magnetization value, okay? So hysteresis curves carry very important and rich information about the magnetization of the materials. And by using the Xrms method, I can investigate the magnetization, the hysteresis curve of each element within the material specifically, separately, okay? This is very important. How to carry out these experiments? Again, you have to fix the theta and 2 theta. Select certain 2 theta and theta angles. How to select these angles? These angles are determined within this X-ray magnetic reflectivity experiment. And then set the temperature, okay, room temperature or higher temperatures, lower temperatures, but during the measurements, temperature must be fixed. Polarization is selected. Then energy is also chosen, fixed for certain element within the material. And by keeping the polarization and energy of the incident light fixed, the magnetic field is scanned in both directions. Okay, this is completely new method of scan, which you learned during this lecture. So what do you see here? I'm talking about the black curve. Energy is selected as 773.4 electron volt around the cobalt L3 edge, and temperature is fixed, and polarization is fixed, okay? Energy fixed, polarization is fixed, temperature is fixed, okay? 2 theta and theta are also fixed, okay? Then I scan the magnetic field. Look at this one. I start from the 0 and I go to the high magnetic fields in positive X direction, and then I reverse the magnetic field and I come to 0 again and I go to the negative side, okay, and then I go to the 0 again. So this is the magnetic field scan, okay? Everything is fixed. I just scan the magnetic field and the intensity is recorded by the detector here. So I reverse the direction of the magnetic field, and I also change the magnitude of the magnetic field during the magnetic field scans. So then here I have hysteresis curve. Here for the cobalt L3 edge, why I did not choose this 780 electron volt, but why we have chosen this 773 electron volt? Look at the cobalt signal here. You can get the hysteresis curve at this energy. Here you can get the hysteresis. Here you can get the hysteresis curve at this energy, okay? So actually I have taken many hysteresis curves around this absorption energy of L3 of cobalt, but here I only present the hysteresis curve taken at this energy, okay? Then another hysteresis curve taken around the cobalt KH or cobalt K energy 726Y. Look at this one, 525. You see, around 526, something like this, 526.8 electron volts, okay, where I see the maximum magnetic signal. Okay, I have chosen this energy. And then I am repeating the magnetic field scan, hysteresis curve measurements for these two energies. So for the black one, for the cobalt, what you see here that the signal is very strong, data is very clear, okay, noise level is very low, then I have very nice hysteresis curve. But in case of oxygen KH, I have very noisy data. You see the red one from the oxygen, data is very noisy. But what do you see here that the general behavior of the signal, the general behavior of the hysteresis curve is exactly same as the hysteresis curve taken for the cobalt. So they are identical. Only the signal from the oxygen KH is weak, noisy, because what do you see here? The magnetic signal from the oxygen is 0.6%, and the signal from the cobalt is around 30%. So then this noisy behavior from the oxygen can be understood. But what is the meaning of identical hysteresis curves taken for cobalt and oxygen? It means that within this zinc cobalt oxide material, cobalt makes bonding with oxygen, okay? And normally oxygen is not magnetic, but due to the bonding with cobalt, okay, it earns magnetic property, and its magnetic property is identical to the magnetization of the cobalt, okay? This tells us that cobalt makes bonding with oxygen within this material, okay? So remember the X-ray diffraction lecture, how this cobalt atoms came into this material. We have implanted these cobalt atoms, okay? At the beginning, we had aluminum oxide substrate, pure zinc oxide without cobalt, and then we have implanted cobalt atoms. Remember the X-ray diffraction course. So what I see here that this implanted cobalt atoms sit on the zinc oxide lattice replaced by the zinc and makes bonding with oxygen. So I have this conclusion. Why? Because the magnetization of the oxygen is identical to the magnetization of the cobalt. And here I also see magnetic signal from the oxygen. This comes from the cobalt-oxygen bonding. So with these measurements, I can understand the magnetization behavior of each element within the material. And in many cases, you can see also many studies. So here you have substrate, and here there is iron. Here, let's say, nickel oxide. Here there is cobalt, nickel, okay. Here there is cobalt, iron, boron, and here platinum, okay. So here each element can be investigated separately, okay, in a multi-layer systems, in alloys. So this method is very powerful, gives us information about the element-specific magnetizations of the materials within the multi-layers and alloys in thin film structures. So with this one, I finished the X-ray resonant magnetic scattering part of my lecture. And next week, we will continue with X-ray magnetic circular dichroism. And I will also explain why intensity goes to detector behaves different for L3 and L2 absorption energies. Okay, this explanation will also be valid for the X-ray resonant magnetic scattering experiments, and you will better understand the theoretical background of this effect which we have investigated today. See you then. Take care of yourself. Bye-bye.